Hi, this is a brief overview of this intrinsic conduction system activity. Most of what you need to know is just in the answers, but I wanted to give some explanation and tie it into some other stuff. So first, when just looking at this first activity, what you want to take away from it is two things. One, you want to know where each piece of the intrinsic conduction system is located. So SA, I won't go over it, but you can see where they're located here. And then know the order in which action potentials are going to travel through the intrinsic conduction system. And it's just like it's outlined here: SA node, AV bundle, bundle branches, and Purkinje fibers. There's some other stuff just to point out. The first thing is this bit right here where it says the SA node spontaneously generates action potentials at a rate of 80 to 100 beats per minute. You may ask yourself, is that what your resting heart rate is? And the answer to that question is no, that is much higher than your resting heart rate. So my question to you is, why is your resting heart rate significantly lower than the intrinsic depolarization rate of the sinoatrial node? The answer to that question is your parasympathetic nervous system. That is parasympathetic tone, wherein postganglionic fibers from parasympathetic ganglia are dumping acetylcholine onto the SA node and slowing down its depolarization so that you're not generating action potentials as quickly. Also down here we see that the AV node does spontaneously degenerate. So it is autorhythmic tissue. Autorhythmic is the word I was searching for there. It depolarizes at a regular rate of 40 to 60 beats per minute. And this we're going to see evidence of later on when we look at some of the ECG tracings from lecture, which I have incorporated into this explanation. So that's this part. I will warn you that I skipped the second page where it asks to decide as a group which part of the intrinsic electrical system serves as the normal pacemaker for the heart. It's the SA node because anatomically that's where the contraction needs to start, and so that's where the contraction starts. So that's not a real big important thing. Then we get just to this, the sequence of electrical excitation in the heart. This also, there is not a lot to explain here. You just look up here at what is depolarizing and then describe what's going on down there. So I won't read over the whole thing, and you don't need to be able to explain the pathway that depolarization takes through the myocardium like this, because we're not doing essay questions. The one thing I will point out here that's important is the pause at the AV node. So that is sort of in between here and here. You have this pause so that following depolarization of the atria, you can have contraction of the atria before the ventricles start to contract. So one of the things I should point out here is when you're thinking about how the heart works, the contraction is always going to follow the depolarization. So if you think about when we did Muscle Tissue and Anatomy and Physiology 1 and we were looking at the graph of the muscle twitch, right, there was that latent period in between actual depolarization of the muscle cell and the generation of tension. Same thing happens here in cardiac fibers. They get depolarized, but then you have to wait for calcium to accumulate in the cytoplasm before you can actually get the generation of tension. So just keep that in mind because it's going to inform some questions later. So then we look at this. This really right here contains most of what you need to know for the lecture exam. It is the ECG tracing labeled along with what each different deflection wave or each wave represents. So it's a lot of what you need to know right there in a nutshell. The only thing I add to this I will get to later actually. So let me just, let's see. So it says question 4, place an arrow on the ECG recording in Model 3 to indicate the SA node generating an action potential. So that would start right here. So SA node depolarizes. That then causes the spread of depolarization through the atria. There is actually what's called an internodal pathway. I think maybe a few conductive fibers through the atria. So that's going to happen just prior to the P wave. And then it says, what does the P wave represent? The P wave represents atrial depolarization. Then our next question, predict the mechanical event that follows the P wave. That would be atrial contraction. You'll also notice you've got this little flat line here in between when the atria depolarize and when the ventricles start to depolarize. That is the pause at the AV node right there. So this little pause in between atrial depolarization and ventricular depolarization is brought to you courtesy of the atrioventricular node. So then it says B in the questions, what does the QRX complex represent? That is ventricular depolarization. I will add that atrial repolarization takes place at the same time as the QRS complex, but it is a electrically small event and doesn't actually affect the QRS complex, and we will have an example of that later on, so just keep that in mind. And then following the QRS complex is going to be ventricular contraction, so that's this flat line right here, then followed by the T wave, which is ventricular repolarization. And right about when the T wave is happening, or a little bit after, that is when the ventricles start to relax. So the atria would be relaxing during this flat line in the QRS complex. Then we get to, and those are all your answers there. This is the part that I really wanted to get to because I think it's what bears some explanation and it's just fun. So let's see, I have labeled them 1, 2, 3, 4. We will go through these questions. One being a normal sinus rhythm. Much maligned Lance Armstrong has a resting heart rate of 35 beats per minute. That is super low. Which recording shown in Model 3 could be Lance's at rest? I say it is number 2. That is bradycardia. Remember, a lower heart rate. So if you're assuming that this chart, each chart has the same time scale on the bottom, then this is beat, 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 and this is beat, beat, beat. So this is a slower heart rate. That is bradycardia. Again, just a reminder, this is normal. Lance is healthy. Bradycardia, not necessarily a sign of pathology, but it could be if there were not a good physiological reason for your bradycardia. Then, when Lance is pedaling up a mountainside, his heart rate is 150 beats per minute. Which recording in Model 3 could be Lance's during strenuous exercise? So that is, of course, number 4, tachycardia. Again, I just like to count the QRS complexes because they're the easiest to see, and they're coming much closer together, So that is a much higher heart rate. Again, not necessarily a sign of pathology, unless your heart rate looks like this when you're just sitting in the classroom, then something is wrong. Let's see. Most people have a change in heart rate associated with breathing, e.g. heart rate often increases with inhalation and decreases with exhalation, which recording in Model 3 shows this condition. That leaves us with number 3. So you can see here, compared to the sinus rhythm, these are kind of far apart. So that's slow breathing as you exhale, and then when you inhale, your breathing increases. The reason why this happens is that you have pressure receptors in your aortic arch, which is in your thoracic cavity. This is to monitor blood pressure, but it's also affected, or they are affected by the pressure in your thoracic cavity. So what happens is your brain actually gets tricked. So normally if your blood pressure goes up, your heart rate is going to go down to keep your blood pressure from keep going up. If your blood pressure is going down, your heart rate is going to increase in response to try and bring the blood pressure back up and keep blood moving. So when you exhale, what's happening is you're starting to compress the contents of your thoracic cavity as your chest elastically recoils and your lungs become smaller. That is increasing the pressure in your thoracic cavity and increasing the pressure felt by the pressure receptors in your aorta, and your brain thinks that your blood pressure is going up, so it slows your heart rate down a little bit. And then when you inhale, you're expanding your chest, you're creating a low pressure zone in your thoracic cavity, which your brain interprets as low blood pressure, and your heart rate starts to speed up. So the question they ask is, how can you determine if you have the condition described in your answer? Do you have this condition? And there are a couple of ways to do it. You could take your pulse while you're breathing. You could get a stethoscope. Or you could just meditate for a while and concentrate on your heart rate and your breathing, and then notice what happens to your heart rate as you alter your breathing pattern. I will also point out, this is one of the reasons why they will say if you are feeling stress, take a few deep breaths. The key to that working is that the inhale is relatively quick, and then the exhale is, you extend your exhale, you sort of clench your throat a little bit so you get some back pressure. That quick inhale, slow exhale accentuates the slowing down of your heart rate during the exhale. And so if you do this, slow exhale, quicker, easier inhale, it will slow your heart rate down. And there is sort of a feedback loop between your brain and your body. So if you are anxious, this will speed up your heart rate. Your brain then perceives that your heart rate has sped up, and that reinforces the anxiety. So if you can bring the heart rate down, it helps to reduce the anxiety because your mind is not responding to your body. It is a very interesting phenomenon, the way that sort of feedback loop happens in a lot of different ways. I won't go into it, but there's other stories you could tell about how that works. Let's see, number 9, it says, people have been known to live without atrial depolarization. What would an ECG look like in a person with this condition? Write a sentence or draw an ECG. So I think we have to go here now. So no atrial depolarization means you are going to have no P wave. So here you have no P wave, QRS complex, T wave, no P wave, QRS complex, T wave. And this would slow down the heart rate too, right? Because now you are relying on your, I can't say it, your AV node, which is 40 to 60 beats per minute. So this would slow your heart rate down. Now your sympathetic nervous system does also innervate SA and AV node, so you could bring your heart rate up if you needed to from whatever the AV node would dictate. So there's probably a role for your sympathetic nervous system to play in maintaining a normal resting heart rate if you have problems with atrial depolarization. Then it says, given that people can live without atrial depolarization, do you think people can live without ventricular depolarization? No, right? Short answer, ventricles move the blood throughout the body. If your ventricles don't contract, the blood doesn't move, you die. That's what it boils down to. I think it is your atria contribute about 10 to 20% of your end diastolic volume, or the amount of blood in the ventricles right before they contract. So EDV is diastolic means relaxing, so end diastolic volume is the end of relaxation right before the heart contracts. So again, the atria contribute about 20% to EDV. So as long as you're still getting a good ventricular contraction, you're still pumping a fair amount of blood. But if your ventricles don't contract, you are done for. Then I just wanted to show you all, and I know we go over this in lecture 2, but it, oh, I can't, hold on, what can I do? Oh, I know what I just want to make this smaller so that it fits in the window. But I can't move my window, so this is the best I can do, is this. But hopefully you all can see this. So here's your normal sinus rhythm. No big deal, no problem, who cares? Junctional rhythm, here we go. This is going to relate back to what we did. Here is the SA node non-functional. So this is that question, if your atria don't depolarize, and it does say that you're at 40 to 60 beats per minute. So maybe your sympathetic nervous system doesn't take over. But it would if you were exercising, so you would still be able to get your heart rate up. Here, this is second degree heart block. So similar to, no, not similar, almost opposite this. So here the P waves don't make it through the atrioventricular node, so every once in a while you are missing a QRS complex. And now I think I have to make this bigger just so we can see. Whoa, that got real big. That escalated quickly. So here you are, P, QRS, T, P, nothing. And then P, QRS, T, P, nothing. I wanted to point out the nothings to show that you have a P wave, which means your atria are depolarizing. And then where your QRS complex would be is when the atria are repolarizing, but there is no voltage change on the surface of the body. There's no deflection wave. So the atrial depolarization is not only is it masked by the QRS complex, atrial repolarization, simply does not show up. Even without the QRS complex, it is not there. And then this, now I got to make it smaller again. Here, can I make? No, I'm not gonna. I'm gonna stop messing with it. Yeah, there's no way to make it good. This is just a mess. This is ventricular fibrillation. AFib, atrial fibrillation, I don't think looks quite that bad. But ventricular fibrillation is an electrical mess. And this kind of electrical activity is not going to lead to smooth contractions. So your ventricular walls are basically just quivering a little bit and shaking the blood, but they're not pumping it at all. All right, that's it. I'll stop there. 20 minutes. I hope this was helpful.